Hello everyone, my name is Szymon Romik. I am software engineer currently focusing on programming persistent memory in C++. Together with my colleague Igor Chorazewicz, we will be presenting C++ persistent containers in PMDK. And here is an agenda for this session. So I will start with a short introduction to persistent memory development kit, PMDK for short. And then I will describe briefly the main features and goals of libpmemobj library and present a short usage example. I will explain then main goals for persistent containers in the library and talk about our design decisions. After that, Igor will present our containers portfolio focusing on algorithms, on media layout, and concurrency issues. So let me start. Okay, you might think that writing software for persistent memory is difficult, and you would be right. This is why persistent memory development kit was introduced. PMDK has evolved to be a large collection of open source libraries and tools for application developers and system administrators to simplify managing and accessing persistent memory devices. It was developed alongside support for persistent memory in operating systems, making sure that the libraries take advantage of all the features exposed through OS interfaces. PMDK is vendor agnostic, open source, performance optimized and tuned set of libraries. Which abstracts away some of the low-level architecture details, like cache flushing instructions, for example. This presentation will be about the library called libpmemobj-C++, and this is a C++ bindings library for library written in C, libpmemobj. Now I will describe briefly the main features for this library. I will start with pool management API. So persistent memory is usually exposed by the OS through a DAX-enabled file system. And memory mapping is used to take advantage of byte addressability of PMEM. However, mmap does not guarantee the address of the mapping, especially if address space layout randomization is enabled. So libpmemobj abstracts away the underlying storage, providing unified APIs for managing files. The entire library adapts to what type of storage is being used and does the right thing for correctness. This means that msync when DAX is not supported. It also works seamlessly for debugs devices. And the pool is a class template where the template parameter is the type of the root object. It supports basic operations like open for opening an existing libpmemobj pool, create, close, and root method. Root method returns a persistent pointer to a root object associated with a pool, but I will talk about root objects later on. Let me now move to the persistent pointer. So like I said, the base pointer of the mapping can change between application instances, and this means any row pointer between two memory locations can become invalid. So we must either fix all the pointers at the start of the application, but it is potentially terabytes of data to go through, or we can use a custom data structure which isn't relative to the base point. And this is exactly what persistent pointer in libpmemobj does. So libpmemobj provides a 16-byte offset pointers which contain of an offset relative to the beginning of the mapping. It is a random access iterator. It has primitives for flashing contents to persistence. However, it does not manage object lifetime and does not automatically add the contents of the object percent pointer points to the transaction, but it does add itself to transaction. Igor will talk more about percent pointer, its optimizations, and the self-relative pointer later on. Another fundamental concept behind libpmobj is root objects. So all data structures of an application should start at the root object. It has user-defined size, it always exists, and it is initially zero. And applications should make sure that all objects are always reachable through some path that starts at the root objects. Unreachable objects are efficiently percent memory leaks otherwise. In libpmobj, we have transactional API, and libpmobj transactions provide ACID properties. So it means atomicity, consistency, isolation, and durability. Atomicity means that the transaction either succeeds or fails completely. Consistency means that the transaction transforms PMEM-OBJ pool from one consistent state to another, and this means that a pool won't get corrupted by a transaction. Isolation means that transactions can be executed as if the operations were executed serially on the pool. This is optional and require user-provided logs. And durability means that once a transaction is committed, it remains committed even in the case of system failures, and this property is guaranteed by the media itself. Transactions in libpmobj are undo log based. So in case of interruption, it is rolled back or completed upon next pool open. The semantics we use took an std function objects as transactional body. So there is no explicit transaction commit when the function body ends, the transaction is being committed. This API is available with every C++ 11 compliant compiler. The transactions throw an exception when the transaction is aborted. They take an arbitrary number of logs and they can be nested. And in this case, when they are nested, the inner transaction is flattened to the outer one. And we have also allocations in libpmobj. We have written our own allocator from the scratch. It is PMEM aware. It is designed to perform best with PMEM and keeps fragmentation issues in mind. The API looks like in this code snippet. We have a function make persistent. The syntax is similar to std make shared. The allocation must be called inside transaction scope. There is also a delete persistent function which deallocates memory, and there are no similar std counterparts for delete persist. So the overall goal of the libpmobj for C++ is to focus modifications on volatile programs, on data structures, and not on the code. In other words, we want you to be able to modify your structs and classes with only slight modification to your function. So here's an example. It is a volatile queue and push method. You can see how many changes are needed with libpmobj C++ to make it PM aware. You basically modify the structures. You started using persistent pointers instead of volatile pointers. You are adding something called P property template class. In this way, the values you want to modify in transactions are snapshotted automatically. And you have to also add a transaction scope to your code to mark range of codes as being executed inside the transaction. Our goal for libpmemobj-cpp bindings is to create a friendly and less error-prone API for persistent memory programming. And even with persistent memory pool allocators, convenient interface for creating and managing transactions, auto-snapshotting class, templates, and smart persistent pointers, designing an application with persistent memory usage might still prove challenging without features that C++ programmers are used to. So the natural step forward to make persistent programming easier is to provide programmers with efficient and useful containers. So code reuse is a common programming principle, and we took it to the heart when some time ago we experimented with persistent memory containers by introducing custom persistent allocator for libc++ STL containers. But as it turns out, there are some hard to overcome obstacles with using existing STL containers. And the main two downsides are first, implementation details. So STL containers do not use algorithms optimal from persistent memory programming point of view. And PM containers should have durability and consistency properties, while not every STL method guarantees strong exception safety. Persistent memory containers should be designed with awareness on the awareness of fragmentation limitations. And the second issue is memory layout. Basically, STL does not guarantee that container layout will remain unchanged in new library versions. So this is why we implemented our own containers with optimized on-media layouts and algorithms to fully exploit persistent memory potential. And their methods should guarantee atomicity, consistency, and durability. Besides specific internal implementation details, PMEM containers have well-known STL-like interface and work with STL algorithms. Since they will extend libpmobj-c++ projects, the goal is to implement them with usage of libpmobj-c++ bindings and make them easily accessible with its interface. Some of the associative containers implemented in libpmobj-c++ are exposed to another PMDK library called PMKV, which is persistent local key value data store, as a storage engine. And in this code snippet, you can see a basic persistent vector usage example. The allocation must be called in a transaction. And after that, you can use it almost like a volatile vector from the standard library. All methods which may alter containers properties use transactions internally and guarantee atomicity and strong exception safety. And now Igor will describe specific containers and will talk about the implementation details.
Okay, thanks, Szymon. So my name is Igor, and now I will walk you through our containers from libpmemobj-cpp. I will also say a few words at the end about performance problems we encountered and some optimizations we made. So as you can see on this slide, we have 7 containers in our current libpmemobj-cpp version, and 3 of them are experimental. So those are the ones in blue. And this means that the layout and API of those containers might change. For all other containers, we guarantee both API and layout stability. And as you can also see, some of the containers are compatible with STL. Some of them have non-standard extensions. So this is mainly true for our concurrent data structures. I will skip describing the most basic containers like string and vector, and I will go and start with segment vector. So the interface for segment vector is pretty similar for std vector from standard library. as you can see on this code snippet. However, it holds data in separately allocated segments and which are never reallocated. It can be used to solve different problems by customizing it using different policies. So you can use it to bypass 16 GB allocation limit, which is currently there in PMDK. You can also use that to limit external fragmentation, or it can also provide you stable iterators. Okay, so as I said, PMOBJ segment vector can be specialized using different policies. On this slide, you can see two different variants of segment vector. In the first one, we are using PMOBJ vector to hold segments, and each segment is of fixed size. This kind of segment vector can help you minimize external fragmentation. Since all segments are of the same size, allocator has a much easier job finding free memory for later allocations. In the second example, we are using fixed size array to hold segments which are vectors. The segment sizes is increasing exponentially, which allows to get better performance. This kind of segment vector gives you also stable indexing operator. And what I mean by that is that since the PMOBJ array is not reallocated, one thread can append entries to the segment vector, and other threads can read all previous elements using indexing operator. So there are no races. And we use this variant to implement something we call persistent TLS. So this is not yet a public API. This is based on TBB enumerable thread-specific structure. And it basically consists of a local, clear, begin, and end methods. The most important one is local. It gives you memory local to a thread. What is important here is that local does not need locks in most cases. So it makes use of the indexing operator of segment vector, and a thread can just read from a segment vector using its ID as an index. Persistent TLS is used, for example, to implement a distributed size variable. This is especially important for concurrent data structures where we cannot update the global size in a consistent manner without locks. This is because we cannot use transactions with atomic variables. So one solution is to use a per thread size, which can be modified as part of a transaction, along with operations like insert or erase. And those per thread sizes can be then summed up on recovery. In our data structures, for example, in Concurrent Map, we also have a volatile global size, which is updated using normal atomic instructions, so that calling size is pretty fast. Other use case for persistent TLS is using it to implement redo lock. I will talk about it later when describing concurrent map implementation. So let's now move on to the first concurrent container, which is PMOBJ concurrent hash map. It uses per bucket read-write lock to guarantee insert, erase, and find methods thread safety. And so each operation in concurrent hash map does the following. It finds the required bucket using the hash, logs the bucket, and work with that under the lock. We solve collisions in this data structure using chaining. And one important feature of this concurrent hash map is that it uses lazy rehashing. So when we reach a threshold, for example, when number of elements is larger than number of buckets, we only allocate a new segment, but do not move the data itself. Instead, all finds and inserts, which end up in this newly allocated segment, detect that the bucket is not rehashed and do this rehashing lazily. And because of that, we can guarantee that the latency remains at a stable level during inserts and finds. Our next concurrent data structure is concurrent map. It is based on a concurrent skip list implementation from TBB, and its average computation complexity is similar to tree-like data structures. for example, B-tree or binary trees. Skip list is basically a multi-layer linked list where the bottom layer is an ordinary list and each higher layer acts as an express lane for the list below. In our implementation, we use locks to implement write-write synchronization. However, for read-write synchronization, we use atomic operations. Because of that, we can guarantee that the search is wait-free. So let's look how the search operation actually works. In this example, we try to find element with key 9. A search begins at the dummy node head and proceeds in the topmost layer until nil or element with a greater key is found. We then descend to the lower level and repeat the procedure. And reading all pointers is done via atomic reads with acquired semantics. Since we are using atomic write instructions for synchronization, we cannot use PMDK transactions to guarantee durability or consistency. And in this case, consistency in particular means that if any node was seen by a reader before the crash, it should still be visible after the crash, even if it was not fully linked. So even if we only updated some of the previous pointers. To solve this, we are using TLS. So when we first allocate new node, we put that in the TLS and only then loop through all the previous pointers and update them to point to our new node. When this is done, we can safely remove the node from the TLS. This operation is safe because even if the whole procedure is interrupted in the middle, we can still redo the operation on restart. In our current implementation, delete operation is not thread safe. So there is a way to logically delete a node from a skip list in thread safe manner, but since our reads are lock-free, there is problem with object lifetime management. There are some approaches which we could use. For example, memory reclamation using epoch-based reclamation. But this approach and also other approaches can significantly hurt search and insert performance. So for now, we decided not to implement that, and so delete operation is blocking. Let's now move on to our single-threaded associative container. So we decided to implement a RadixTree, which has some nice properties for persistent memory. And for those who are not familiar, RadixTree consists of internal nodes, which hold array of pointers to children, leaf nodes, which contain the key value pairs, and edges, which represent parts of the key. And we use those parts to navigate through the RadixTree. To find an element, we just take the first character or byte of a key and use that to index the children's array. We follow the edge to the child and proceed with the next byte. As you can see on this example on right, for Romulus, some bytes might be skipped if there is no ambiguity. And this is called path compression. So in some circumstances, edges can represent multiple bytes. And the important characteristic of RadixTree is that there is no rebalancing. In some cases, when there is a path compression, we might need to split an edge. But even in that case, this is only one extra allocation and one extra pointer swap. So this is not so costly as rebalancing in B-tree or binary trees. Also, notice that we only need to compare key twice, not log n times like in tree-like data structures based on comparisons. The first comparison is done when we are descending the tree to compare with the edges, and the second time is needed when we are actually in the leaf to make sure this is the element we actually want. Because due to the path compression, some bytes might actually be different than our looked for key. The RadixTree implementation is mostly compatible with std API for std map. The difference is for iterators, and obviously we don't have a comparison template parameter since this is not comparison-based data structures. You can read more about API in the link below. On this slide, you can see an example where we use RadixTree with PMOBJ-string as a key. We do that because we want to store some dynamically sized data. Similar to std string, PMOBJ-string stores its data on the heap. However, as we all know, persistent memory has higher latency than DRAM, and we want to limit number of pointer dereferences and allocations in our algorithms. So for that purpose, we introduced InlineString. This data structure can hold data within the same allocation and hence limit the number of dereferences. On the right, you can see a layout of leaf node for RadixTree when we are using InlineString. And you can see that all the data is stored within the leaf in the same allocation. And by the way, both key and value can be inline strings. Okay, so that was the last container I wanted to talk about. Now I will say a few words about a persistent pointer performance problem. So we got a report some time ago that the referencing our persistent pointer is very slow compared to regular pointers. And this is true especially if you do that in a loop, and you would expect that the compiler should optimize the code and there should be no significant difference between persistent pointers and regular pointers. However, it turned out that because of the way our persistent pointers are implemented, compiler has very little optimization opportunities. So on this slide, you can, in the code snippet, you can see the simplified version of persistent pointer implementation. As Szymon already said, persistent pointer contains of two 8-byte fields. One is pool ID, and the second one is offset within this pool. The PMOBJ-direct method, which you see below, is called every time either the references our persistent pointer. Inside, you can see that we use TLS to cache base address of a pool, which is necessary to avoid costly calls to PMOBJ pool by OID, which is lookup in some tree-like data structure. Because we always read the TLS value, compiler is not able to optimize access in a loop, for example. In this regard, TLS value is actually very similar to a global value, which can change at any time, also by another thread. And so compiler is not able to optimize this read out. To fix this problem, we introduced a new type of pointer, which is called self-relative pointer. So the main idea here is not to store the absolute offset of the data, but rather only a distance between the pointer itself and the data. On this image, you can see a pointer inside object A, which points to the object B. The value stored inside the pointer is 2000 because that's the relative distance between the objects. To get a regular runtime pointer, you have to sum up the value of the pointer with the address of the pointer itself. And you can see that in the code snippet below for the get method. Implementing pointers in such a way makes compiler optimizations possible. And in our benchmarks, the referencing self-relative pointers is basically as fast as a regular pointer. This can differ in different circumstances. So some compilers might do a better job optimizing, but in general, this should offer much better performance than persistent pointers. Moreover, for self-relative pointer, we only use 8 bytes instead of 16. Of course, there is a drawback with that. With this kind of pointer, you can only reference objects within the same pool. And we got to the end of this presentation. And to sum it all up, designing efficient data structures for persistent memory is quite a difficult task. However, you don't have to do it all by yourself. You can use libpmemobj-cpp containers, which are already well tested and optimized for persistent memory. You can also use most of those data structures, especially RadixTree concurrent map and concurrent hash map through PMDK, which is a key value storage. And you can also use that through bindings to Java, Python or Node.js. On this slide, you can see several links which you can go to. I also recommend taking a look at the last link, which is a persistent memory programming book, which has a lot of useful knowledge about designing data structures and general persistent memory programming. And that will be all. Thanks for your attention.